So our next speaker is Orion Papadakis from Manchester University, and I'll hand over to him. Thank you.
Thank you. Hello, everybody. I'm Orion Papadakis. I'm a research associate in the University of Manchester, working on the Tornado VM team, which is a managed runtime for heterogeneous hardware. I joined the University of Manchester back in 2017 for my PhD studies, and part of this PhD is the work that I'll be presenting you today. First of all, I would like to give you an outline of this presentation. Initially, I would like to introduce you to the problem and the research gap we found, and then I would like to explain to you the strategy we follow and the tools we used. Next, I would like to present the two core parts of this work, which is, the first one is the NUMA scalability study, and the second one is the optimization that we propose. NUMA is an acronym for non-uniform memory access architectures and has been introduced in order to enhance the scalability over hundreds of cores and gigabytes of memory. It is a node-oriented architecture, which means that it is composed, a typical NUMA system is composed by nodes, and each node contains CPU cores and memory, and the memory can be accessed by any core across the nodes, but with increased and different latencies. Consequently, this design poses new challenges to the programmers in order to write software that benefits from NUMA, because the programmer needs to be aware of the underlying hardware and the memory topology. Especially when we talk about a managed application, managed software, for example, Java, which run on managed runtime. For example, in Java, they are hosted by a JVM. This challenge becomes extremely more difficult because the managed runtime automatically manages the memory, and secondly, the programmer has no control over it. Among a lot of related work, studies, efforts can be found in the literature that have focused on this problem, on how to improve the scalability of managed applications on NUMA architecture. And most of those works converge to the perception that the main bottleneck on this problem is the unoptimized components of the managed runtime systems, for example, the garbage collectors, which are not aware of the NUMA hardware. Hence, they need to be optimized in order to achieve better performance and scalability. And indeed, they have provided amazing results, and they have improved performance. But we argue today, through this work, that this is only the half-truth. And because the other half-truth is that not only the garbage collector is a bottleneck for a managed application on NUMA machines, because also the mutation, the non-GC time, is penalized when run on a NUMA machine. And to comprehend this, we run almost all the Capo and Renaissance applications with Maxin VM on a NUMA system with two nodes. And in this figure, we can see that the mutation time is penalized in almost all applications. Some of those are, this is critical. Consequently, a natural question that arises by this observation is under which circumstances NUMA is beneficial for a managed application. And here comes our approach, which is, first of all, to study and characterize a large set of managed applications from the Capo and Renaissance benchmarks in order to understand why some applications are not able to scale, why some other can scale, and find and draw a conclusion under which circumstances NUMA is beneficial. And as a second step, to leverage those findings in order to provide a better solution. In our case, we propose an online and application-agnostic optimization. To conduct this study and to prototype the optimization, we use MaxNVM as the management time of choice. MaxNVM is a research VM written in Java, which means that provides easiness in development, in prototyping new things and that stuff. And also, apart from this, it contains two very useful tools, the Perfutil and NUMA Profiler, which are very useful in profiling an application, especially in the context of NUMA. Perfutil leverages the hardware performance counters in order to provide metrics such as the CPU cycles, instructions, metrics related to cache hierarchy, LSE misses, and that stuff. While the NUMA Profiler probes the runtime layer of MaxNVM in order to provide metrics related to object allocations, object accesses, shared object accesses, and information regarding Java threads, and more. In order to conduct our NUMA characterization study, the goal of this study is to examine those properties of an application that are related to scalability. Those are the serial code sections, the load balancing, the contention on shared resources, and data locality. Based on those properties, we formalize our study in 3 steps. The first one is to assess and evaluate the parallelism and balance. The second one involves the data dependencies. And the third one, the data locality. So, if we take each step at a time, first of all, we evaluate the parallelism and balance of those applications using several key metrics. Some of those are the number of worker threads and the imbalance that an application exhibits in CPU cycles, in hardware instructions, and the object accesses. It is notable, and I would like to share with you, that examining those three metrics, the imbalance in cycles, instructions, and object accesses, it is this assessment can highlight whether an application is memory bounded or compute bounded. It is very useful. So, using all those metrics, we characterize all the applications that we focus on, and we find 5 categories: the single-threaded, which is obvious, all the applications that use only one thread; the TLB-bound category, that we classify all applications that use less worker threads than the available CPU cores; the imbalanced applications, that are those applications which spawn a lot of threads, but actually the work is carried out only by 1 or 2 threads; the imbalanced applications that exhibit a lot of imbalance; and the explicitly parallel. Second one is the assessment of data dependencies. Here we use the metric of shared object accesses, which is provided by NUMA Profiler, and essentially is based on the heuristic that if a thread that is not the owner of an object accesses this object, this access is classified as shared. And using this metric of shared object accesses, we classify again the objects, the benchmarks, in those that are data parallel, having no read or write dependencies, having no shared reads or shared writes; those who have both shared reads and shared writes; and those who have only shared reads. And it is notable that even though an application can be characterized as having only shared reads, this application might behave either as data parallel or like having both read and write dependencies. And the third part of the study is the assessment of data locality, where we use the metrics of the LLC miss rate and the remote node accesses. For the LLC miss rate, we compare the observed LLC miss rate when running the application on a single node, let's say in a non-NUMA environment, and in two nodes in a NUMA environment, and we observe the difference, and the remote node access as well. And we gray out those applications that have been found as data locality bound. And as you can observe through this table, we have merged all the previous categories that we have found in one table. On the y-axis on the left, we have the data dependencies, the categories of the data dependencies. On the x-axis, we have the categories of the parallelism. And on the y-axis, on the right, we have those are locality bound. And we merge those three steps of characterization in one table in order to form the NUMA scalability characterization table. Finally, as a final step, in order to cross-validate this table and this characterization, we measure the actual performance of those applications when we let them to scale on the NUMA machine. And what we find is that mostly the applications, except the explicitly parallel category, are, as expected, not able to scale very well. But the important thing here is that the explicitly parallel applications, we observe differences among them. Some of them are able to scale, some of them are not. So this is like a gray area that we are not able to know beforehand whether this application, an application that is categorized as explicitly parallel, can scale or not. We can take a step back from from the study and think how we can improve the situation based on those things we have found. First of all, we have a tool, the Perfutil I told you earlier, that operates in very low overhead. And we have a study, we have conducted a study that provides a lot of hints on what to expect when running one of those applications. And having those, we can consider, naturally consider, what if we implement a new mechanism that can be online because we have the low overhead tool and application agnostic in order to improve performance. And based on this, let's say, vision, we implemented the prototype, actually, an optimization mechanism that is indeed online, performs online profiling and decision-making. It sleeps, it iteratively takes decisions, sleeps for 200 milliseconds, takes the profiling, processes the profiling, and then decides. Actually, the decision answers to the question, should I scale this application or not? And the evaluation of our mechanism shows that it improves performance by 11% overall and ranges from 0.66 times to 3.3 times. In addition, we have added the feature of stabilization because when experimenting with the mechanism, we observed that there is a heuristic that we can use, that a repetitive decision is less likely to be a coincidence. So, for example, if we run an application and iteratively decide what to do, and we always take the same decision, we increase the frequency of the decision making in order to minimize the overhead of the mechanism. Anyway, I have put also an abstract, a figure of the mechanism, but you can find a lot of details, of course, in the paper. And this is the evaluation for all applications that we experiment with. An important thing here is that we see that the most benefited applications are those that were the most penalized applications that I showed you in the beginning. So our mechanism is able to take back the performance penalty. And most applications are benefited, 26 out of 30. Some of those that are not benefited, we find that they have different phases in the execution. So, and this fact blocks our mechanism to adapt into these phases and take the correct decision. And this is something that might create future opportunities for a better mechanism. To summarize, we have provided an approach that, to improve performance. It is complementary to the state-of-the-art papers that address the same problem, the NUMA scalability study, and the optimization approach. Thank you very much.
Thanks very much. If you'd like to ask a question, please come forward and use the mic and introduce yourself. Questions?
Thanks for the talk. I have a question regarding the profiler part.
Yes.
So is that sampling based like length curve in this specific VM?
So we have two profilers. Yep. First one is the perfutil that handles the hardware performance counters, like the Linux perf. And the second one is an object profiler in the VM. And this profiler traces keeps a record of every object allocation, every object access, and whatever, you can actually track whatever happens in the runtime.
I see. A quick follow-up question. So did you try to like play with if we have more, like, for example, if the sampling frequency is higher, meaning we have more accurate profiling data, does that help the results? Or maybe the other way, if it's less accurate, does it hurt the performance?
Yes, we played with this parameter, and this is the 200 milliseconds that I told you that the mechanism operates. And after experimentation, we found that this frequency is okay for the results.
Hello, thanks for a nice talk. A quick question about predicting the future. So 10 years ago, everyone said, NUMA, we'll all be using NUMA, but we're not really, are we? Is NUMA take-up quite as rapid as you might have expected it to be?
Well, I don't have a strong opinion on that. I believe NUMA is a nice concept for scalable systems. And I see that in 10 years from now, we probably will still use NUMA.
All right, well, thank you very much for a great talk.
Thank you.